All right, let's get going. So good afternoon, everyone. Same drill, laptops away. If you guys need to leave early, please sit in the back. So we got a ton of material to go over today. So we're going to be cramming. You guys amped for more pointers, some stack and some heap. I get super excited about this stuff. If I had to choose between like racing motorcycles for a career and learning about stack and heap stuff, I probably would be in school. But if I had to choose between like chewing on glass and eating Tabasco sauce and learning about this stuff, I might learn about it, maybe. Maybe not. So when we left, I'm gonna go through a quick recap from Monday, because pointers need to be fresh in your brain for when we go on to stack and heap stuff. So this is going to be crash course. So hold your questions to the end of it. It's going to be recapped here in class. So we looked at what a model of a computer looks like, and specifically what memory looks like. So you've got a big chunk of memory here for program data, and then you've got a big chunk of memory that actually has your program in assembly form. It's all just ones and zeros. Memory is indexed from 0 up until 2 to the 32, 32-bit system. And then we looked at how CPU actually runs the program. It reads an instruction out of memory. The instruction says, pull these two values as integers and add them together. So it goes into memory, grabs these two addresses as integers, aka 4 bytes, loads them into the CPU, adds them together, and then we say, store the results at this address. And that, of course, is the start of that address. So it's OX6F blah, 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 B0, all the way up through B3, those 4 bytes there. So there's our modified data right there. And then the CPU automatically goes on to the next instruction. So that's taken care of for you. And CPUs just execute from top to bottom, instruction after instruction after instruction. There's instructions that allow you to jump back up to another instruction somewhere else or down. And those are how you implement things like functions, if statements, while loops, all that kind of stuff. But as the CPU cares, it just executes things linearly. And that's a single core, of course. So then we got into the ampersand operator, which is the address of operator in C++. And it allows you to take any variable in your program and say, where does this exist in memory? And that'll give you a number at runtime of where it exists in memory. It's not quite predictable ahead of time, the exact address. But what is predictable, if you have two variables next to each other, they're going to be off by 4, for example. If they're ints or floats or anything with a width of 4. That's predictable. The exact address of where it lives is not predictable. And that's done for security reasons. So we looked at this clicker question, and the answer to this one is D. So you start off with a long value. I assign the value to it, 42. It's just standard long, just like an int, except it's 8 bytes. And then we take bar, and we get the address of food using ampersand. And then rather than storing it as a pointer, we were just kind of hacking things. I'm just going to store them all as integers. So I stored it as a long, and this is, of course, a cast to a long, just to coerce the C++ into doing this for me. And then I spit out the value of the address of bar cast to a long. The trick, of course, is that what bar is equal to is totally irrelevant. All I care about is the address of it. So the answer is D. And then we started looking at how to store pointers. So we could theoretically go through everything and store them all as longs, and that gets really messy. What does this function take in? A pointer to what? And you could do the kind of Python thing where you do everything in comments, or your variable name is kind of self-explanatory, like a pointer to a float is your variable name. But that's not how C++ is done, because C++ is statically typed. Everything needs to be known ahead of time. And Python, by the way, if you guys are wondering, it knows the difference between an int and a float. Remember that slide I was asking how C++ knows the difference between an int and a float in memory? Python actually does do one of those other options. It either stores what that is in a table somewhere and looks it up before it uses it, or for every single data value it stores a little key in there that says this is an int. I suspect it uses the table thing because that would be a lot faster, but I actually don't know. But it does have to store extra information, every single piece of data, so that Python knows this is an int, this is a float, this is a string, char, what is this? So rather than doing the long thing, we got into actual pointers in C++, which is this little I'm going to try not to say ampersand this time. The asterisk. So it's a star right behind a float. And then we got into how to read these things. So whenever you see stars, read them right to left and replace all the stars with the words a pointer to. And then the last thing with, hang on, whatever the data type is. So it's a pointer to a float, which looks like this. So this whole thing is called my crazy type. The whole thing itself is a pointer to a float. That's its data type. And a student came up on Monday and was talking about this too. It's actually a good way to think of, when you do pointers to stuff, think of it as its own type. It's no longer a float, it's not an int, it's its own type. You just created a new type. And the type of it is pointer to a float. So it's its own type. If you try to assign that type to an integer, C++ is going to complain at you very vocally. Other way around, same thing. The types need to match, just like you guys have done with types before. You can't assign a double to a... I feel bad saying this because a lot of this you can't actually do. But you shouldn't assign a double to an integer. C++ will let you get away with some pretty terrible stuff, actually. So we looked at a little bit more of what the clicker question looked like in memory. So you've got foo. Foo actually exists in memory. It's got a value. It's set to 42. Bar actually exists in memory. It's got a value. It happens to be set to the address of where foo lives in memory. And then same with baz, except for pointing to bar. And then we looked at what this looked like in memory. So foo actually has the value 42 in there. Bar has the value of the address of foo. And then same with baz. So then we got into how to use pointers. You've got these pointers, and that's great. Now what can you do with them? A pointer in itself is not very useful if you can't jump through the pointer. You can't say, I no longer care that this is a pointer, I want what this thing's pointing to. And that's where the star operator comes in, also known as the reference operator. And then I gave you guys a word of warning. Be really careful on this stuff because it's used in at least 3 places that I can think of off the top of my head. There could be more. So pay very close attention between this one here and this one here. Notice that this one has an int, a data type declared in front of it, and this one does not. It's a big difference between those two. So be careful of those. And then where we left off on Monday was I was threatening kittens. So now we're going to continue with this clicker question. And where did my clicker thing go? All right, a couple more seconds on this one. So let me pause this and I'll show you guys what we have for results. I'm going to come back to this question. Very unsure. If we have any majority here, it's C, the address of bar, but there's a lot of confusion between A, B, and C. And then maybe a little tiny bit of D. So I'm going to come back to this question. Let's look at the next 2 slides and see if we clear things up. We have 2 operators here for pointers. 2 operators to do things with pointers. You can either create a pointer, or you can dereference a pointer. And then we also have something to store pointers, which is actually a different thing. So the ampersand, think of it as adding 1 jump. This is a float right here. If I want to take this float and I want to say, I no longer want the float, I want something else that just points to this float. I use the ampersand operator. And it creates a pointer to what's here. I could do that again, and if I use this, then I'm creating a pointer to points right here. And I've got a double pointer like I did with the bottom line there. I could also, this is a float, say give me a pointer that points to the float, and then I could get another pointer that points to the float. So now I've got 2 pointers pointing to the exact same place. That's totally fine to do. So if you think of pointers as jumps, going through jumps to try and get to something, think of ampersand as adding a jump. I want to add in 1 extra arbitrary jump in there. No, ampersand. I'm actually using the right one here. Yeah, ampersand's the and sign. Right? Yes. Okay. Yeah, ampersand. Think of the ampersand as adding one jump in there. An arbitrary extra jump. Think of asterisk, the star, as removing a jump. Or you could think of it, if you want to think of them as jumps, you could actually think of it as going through one of the jumps. So if you've got a pointer to, say, an int in this case, if I no longer want a pointer to a pointer, if I no longer want a pointer to an int, I can dereference it once, and it gets rid of one of those jumps, one pointer. So now, I just jumped over one spot, and now I'm just a single pointer to an int. Now if I want that actual integer, I can dereference it again, and now I'm the actual int itself. And now I could change the integer's value if I wanted. Yep?
So when you say it removes one jump, how dependent on that is where it is in the set? So is it after the int, before the baz, does that make a difference when it removes? And if you have both that and the ampersand at the same line? How does that work?
Sorry, I'm not following.
So when you say the ampersand adds a jump and the star removes one jump,
right?
And you have them both in the same line of code, how does that play?
Oh, this is just the last line of code from the previous slide right here. So if we look back one slide, baz is equal to the ampersand of bar. So I just copied that same line that you saw above. This top line here and this bottom line right there are the exact same thing. And then these two right here are the first thing where we start dereferencing. So we dereference a pointer to a pointer, and then we end up with just a pointer. And then we dereference the pointer, and we end up with the original thing. To answer your question? Okay, yep. No, equal to is a Boolean operation. It says, are these two things equal? This is an assignment operator. So I'm assigning the value of bar2 equal to b, whatever, and this is where we're actually using the dereference operator. So what's getting confusing, I'm going to guess, is what I was hinting at on that slide before. You're seeing this star bar2 and then this star baz. And they look really familiar. I mean, they look really similar, excuse me. But they're different. The star int is declaring a new data type. I'm not creating a new data type that is a pointer to an integer. And what I'm assigning to this variable of that data type is the dereference of baz. So baz is a pointer to a pointer. So I could not possibly assign that to a pointer to an int, right? So what I do is I dereference it once. I jump through one of the hoops. And now what I have left over after doing that jump is just a single pointer to an int. Yeah?
On the first line, what if we had two ampersands instead of just one?
I actually have no idea. You can do two asterisks, which just jumps through two hoops. But here's the catch in doing two ampersands. And C++ might let you do this, but you've said, let's say this is an int. I want to now create a pointer to it, but before I've assigned this pointer to anything, I'm now creating another pointer. So what I don't know is where C++ is going to put this middle pointer in memory. It may be possible, and they may have some little trick for it. Seems like a pretty terrible thing to do. Because now you've just got a double pointer that's totally useless. Yeah?
So star baz points to food.
Star baz points to the address of food. Yeah. So if we look back at this slide right here, foo is 42. Bar is the address of 42, foo. And then baz is the address of bar. So if we just go back, if we have bar and we go back one step, what we're left with here is the address of foo. So yeah, you can literally think of it as walking up this chain from here back up to here. And that's exactly what we did, except in reverse order. Starting here and then walking back. Yeah? So what's wrong with saying int foo equals and then some string? What's wrong with saying that? Yeah, they're totally different types. They're disparate types. They cannot be reconciled. And the exact same thing happens in C++. Every time you use this equal operator, you have to have two types that are the same. So what is on the left side of the equal sign, the star bar, has to be the same type as what's on the right side, which is the address of foo. They're both single pointers to integers. Now you can set them equal. Nope. Just the way pointers work. Okay, so let's go back to this question then, not the dreading kittens. All right, chat with your neighbors and revote on this one. Armed with your new knowledge. In a little bit. Okay, look what we have. Much better. Okay, so line by line, we've got foo, which is an actual thing. Good job. Wow, now the percentage is increasing. It's amazing. So we've got foo, it's an actual thing. It's got an integer in it. It's got the value 42 in it. Then we create bar, which points to 42. Then we create baz, which points to bar. So now we've started off with foo. Foo's got a pointer to a bar. Bar has a pointer to it called baz. Now I'm going to dereference baz once. One step over. What am I? Right, I'm pointing to foo. I'm the first pointer there. I am bar. I am the address of foo. Welcome to pointers, guys. Some of you are going to go home and start eating glass and chewing Tabasco sauce instead. All right. So more into pointers. Let's get into some slightly more useful cases of pointers. Let's get into strings, or C's really lame excuse of string. C++, of course, you guys have seen the std strings built into the standard template library. Please, when you're writing real code, use those. They're like a million times better. Yeah?
I'm sure we thought of this before. Why do we care about the address of something in memory? Don't we write programs to like do things for us, like, and the address is just where things are stored? Why do you care about the actual slot itself?
Is this like a philosophical question in terms of why don't we make a language that does it for you, or in C++, why do we care? Because C++, the compiler goes through and reads your code and generates actual assembly instructions. It's actually called a compiler. So, for example, Java. Java does not compile code down into something that your CPU can run. It compiles it into something called bytecode, which is an intermittent language. To compile code down into something that the machine can run natively, that your CPU can just sit there and chug away on, you have to explicitly declare, this is an int. And you have to think about the fact that the compiler needs to put this somewhere in memory. It can't abstract it away from you because it needs to be able to generate assembly code. Now, if you do something like Python, Python's interpreted, Java is compiled down into an intermittent language, and then it's called JITted later, just-in-time compiled. You can do something like that. You don't need to worry about where things are stored in memory. Those are called managed languages. They manage the memory for you. There's no such thing as a pointer in Java. Now, C++ is an unmanaged language. It exposes raw memory to you. So C++, you have to think about memory the way that it actually is. You can't think about it as Python thinks about it, and you just make some variable and assign whatever on earth you want to it, and it exists, who cares? You actually have to think about it, because it's unmanaged. And that can be really powerful, because you can write really fast code. And for example, a lot of the graphics work that I do, graphics work in a managed language, something that manages memory for you, is a disastrous mess. Because graphics, you need to create this really complex chunk of data in main memory that has to be laid out perfect, byte for byte. It has to be absolutely perfect in the exact right spot. Then your graphics driver takes that chunk of memory and loads it into the graphics card memory. That memory has to be perfect. In a managed language, a lot of languages don't even allow you to lay memory out manually. They just do it for you. So it can be very useful. As a practical language, C++ is not going to be your most productive thing in most cases. Because you have to constantly think about where does this exist in memory. And that's just like mental overhead you don't need for 99% programs. It's a good philosophical question. But C++ also runs really fast. Okay, so let's get into C strings. This is before C++. These are still used everywhere in C++, but these are before the std strings. So in C, when you declared a string, it was nothing more than an array of characters, one after another. Now you guys will notice here, char star, that's my variable name, because it's a gross C string. So why the char star? Why is an array a pointer? Like I thought a pointer was a thing that points to a single data type, like an int or a float. But this is also how arrays are done. And this will eventually make sense. For now, it's probably just going to cause you lots of brain damage. Next slide. So if we take this chunk of code here, char star ugh equals done, so it's done, and we stick it in memory, what that ends up looking like is something like this. Notice the addresses are off by 1 here. They're no longer off by 4, so these are different than what we were looking at before. They're off by a single byte. And we have the number 86, 117, 109, and 98 sitting in memory. 1 byte after another. Now, we could choose to interpret those as numbers. We could choose to interpret all 4 of them as a single 4-byte integer. We could choose to interpret those 4 as half of a double. But we're not going to, because we told C++, choose to interpret these as chars, as characters, which it kind of handles sort of nicely. Now, do be aware when you guys are looking at diagrams online, there's something called big endian and little endian. We're not going to go into what they are, but if you're looking at how character arrays look in memory, they might look a little different. They look similar, just kind of messed up, like someone went in there and did something funny with them. There'll still be a solid chunk of memory of characters in them. Okay, before we get to code, is there any questions on that? Yeah, they're asking. Yeah. And you guys can, I don't know if you know this, but in C++, you can just take a char and just cast it directly to an int or a long, and it'll tell you what the actual number value is. They're represented as unsigned bytes. Okay, let's look at some code. Where did we go? So on the same vein of C arrays, make a nice long string here. Now, Xcode is probably going to give me a bunch of warnings because this is unsafe code and it doesn't want you to do it in modern C++. This is old school C. I could fix this, but I don't feel like it. So let's do this. Let's see out ugh. What does it print? Predictably, it prints dum, 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 dum. But what's happening here is ugh is only a pointer to an array of characters. The stdcout and these stream operators know how to handle a pointer to an array of characters. There's also something hidden going on here, which is there's a hidden character right at the end of this string, which has the integer value 0. It doesn't print to anything. The integer value 0 has no equivalent character. It's not like an A or a C or a capital G or whatever. It doesn't print anything. It's special, it's reserved to say this is the end of a string. So what I could do instead, if I wanted to print this out, let's actually do some manual pointer arithmetic here. Let's print out, I don't want to do this. Let's do this. And actually, before we run this in a loop, what are you doing, Xcode? See, sometimes IDEs can be a real pain in the ass. Before we run this in a loop, let's actually just run this by itself. So what should the dereference of a pointer to a character array be? What should this print? You guys have hypotheses on this one? Hypotheses? D? You guess? Anything else? D? Bueller? Bueller? Anyone? All right, let's go with D then. See what it prints. Sure enough, it's D. Because the pointer into this array of characters points to the first character, always. It always points to the first byte. So if I dereference, here I am, I'm a pointer, pointing to a character. If I dereference, go through one jump, I'm now pointing to the first character. Now let's say I wanted to use the same trick to print out all the characters. So first we print out ugh. If I run this as it is right now, it's going to print out D forever. So at the bottom of it, let's take ugh, which is a pointer, and let plus equals 1 to it. So what's this going to do? Here's my pointer to a character array. The array is actually a whole bunch of bytes in memory. I'm just pointing to the first one. So I'm going to first dereference it, print out this. Now I'm looking back at the pointer to it. I'm going to advance the pointer by 1 byte. So now what is it pointing at? pointing at the next character after the first heap. Now let's run this and see what we get. We're going to get something a little unexpected. Whoa, what's going on here? I get a whole bunch of garbage. But if I scroll all the way up to the top, I can see DUMB, dot, 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 DUMB. If I get rid of this ST and L, this will be a little easier to read. Except for all the garbage, of course. There we go. Dum, 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 dum. So the last thing to do is, and this is proof that that 0 actually exists, let's now say if the character that we're pointing to equals 0, then break. There you go. So now, using direct memory manipulation, we just printed out each character in a character array. Yeah?
That is an array. How do you initialize?
I'm going to ignore that question until the next slide, because that will be explained. It's a great question, actually. So there's also a C++ way of doing this. I'm going to comment this out, because this code destroys my pointer. It advances my pointer to the point where my pointer no longer points to the beginning of my string. So I'm going to comment that out, and we'll do the kind of C++ way, or this is actually in C as well, way of accessing this. What I could also do is, because UG is an array, let's do the exact same code, UG, so this is a for loop that starts off at 0, advances I, and just runs infinitely. If UG, and then you guys remember this notation here, these square brackets, this is an array access operator. So this is built into every language that I know of for accessing arrays. And it accesses the ith element in an array. Now this operator is a little bit more clever than just directly adding onto a pointer, because it knows that chars are exactly 1 byte. So when I advance by 1, it needs to add in a single byte. If, for example, I had an integer array that was 4 bytes wide in each element, if I advance by 1 element, it's going to know to add in a full 4 up to that point. This is called pointer arithmetic. And this thing behind the scenes does pointer arithmetic. And it actually compiles down to the exact same code that the machine runs if you did what I did above. It's going to do something very similar. It might find a more efficient way to do it. Because compilers, by the way, compilers are absolutely amazing things. They come up with optimizations you'll never think. So then I can also take UG, access the ith element of it, and then that's all I need to do. I don't need to advance the pointer. So theoretically, if I run this, I get dum, 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 dum. Very exciting, huh? So let's see, how are we doing on time? We are already running so long time. So I was going to show you guys what this looks like if you have a float star. I'm going to skip that because it's actually a decent amount of extra code. But the principle is the exact same. You've got a pointer to a float, and that first float just happens to be the first float in this array of, I was going to make 4 floats. And then you can do pointer arithmetic and add 4 in each time, spit out the float, or you can use the array operator to access it. Like this. I'm going to skip that for now. Yep.
Why are we only adding 1 of the chunk?
Because how wide is a character? How many bytes is a single character?
It's only 1 byte.
Right, it's only 1 byte, yeah. If this was an integer array, we'd have to add 4 in each time, or we'd be totally messing things up. Okay, so remember earlier I said this is your program's data, and this is going to come back around and answer your question at some point. And I said on Monday that this is actually split into 2 distinct parts. We're now going to learn what those 2 distinct parts are. The stack and the heap. I'm sure you guys have heard of these before and probably just don't know what they are. The stack always starts at the highest address. And then we'll see this later, but it starts growing downward. The heap's the exact opposite. It starts off at the lowest address and starts growing upward. Siri's not very good at computer science, it turns out. She just doesn't get it. All right. So here's a nice picture that I just shamelessly ripped off from the internet, because I didn't feel like making it. So this is the stack. Remember, there's the 2 pieces. You got your stack, and you got your heap. Stack grows downward, heap grows upward. This is the stack part of it. Now when your code's running, remember you just have this big giant byte array. That's all memory is. That's what stores everything your computer ever does. Everything it ever thinks, every game it ever plays, everything. It's all in memory while it's running. The stack is responsible for keeping track of what function you're currently calling and what local data that function and every function before it has. So remember I said the stack starts off at a big address and then it grows downward. What I mean by growing is every time someone calls a function, a new frame gets put on the stack and it gets put onto the bottom of it. And that frame is only removed from the stack once the function is done executing, aka once it returns. Now, the stack is pretty much free to use. You could allocate a kilobyte of memory instantaneously. It's free to use, but you have to know exactly how big the frame is going to be at compile time. So it's got a huge drawback. Let's say you're trying to ask for user input, and you have no idea how much the user is going to input. How would you make a stack frame for that? Maybe you make a stack frame assuming that I'm going to enter 512 characters, and I enter 1024. Now, you guys are all like super into hacking, so what I just said is the basis for the most common hack on Earth. Someone who's coding makes a stack frame that's assuming I'm going to enter 512 characters, but I don't. I enter in more than 512. And what happens is I start writing over the top part of the stack with whatever I want to put in it. And I can carefully structure my string to do exactly what I want it to do. And you can actually hijack a program doing this. So I know you guys are just obsessed with security and stuff, so that's one of the biggest, if not the biggest security hole on Earth. So before I take questions on this one, let's actually look at what this is in Xcode. So Xcode has a debugger built into it, which I actually haven't shown you guys very much, but it's an amazing, amazing thing. So I'm just going to make 3 functions here. You'll notice they're in reverse order because now they're in reverse order because C++ is too stupid to read below what you're trying to execute. And in function 2, I'm just going to call function 3. And then in function 1, I'm just going to call function 2. And then in main, I'm just going to do nothing but call function 1. So this is a really, really uninteresting program. It's going to call function 1. Function 1, before it finishes, it's going to call function 2. Function 2, before it finishes, is going to call function 3. Now, I'm going to make a breakpoint, which tells Xcode when it gets to this line of code, when it's executing, please stop and let me look at things. Okay, now there's 2 things to note here. One, right here, this is your call stack. It is your stack frame, like this, except it only shows the data of what function is currently running. It doesn't care about the actual data, local variables, things like that. It only shows you the function that you're currently in, which is stored in the stack. It's stored in a stack frame. So we can see here there's 2 things that we don't even know what they are. They're called start. And then finally our main got called. Now main, this is the other thing to note, has got these local variables. If we were to inspect the stack, we'd actually see these 2 variables sitting on the stack. They exist in this stack frame for main. To make a little bit more sense, when I do debug step into, that steps into the function that I'm about to call. So now you can see execution just paused right here within function 1. Look what happened to our stack frame, or call stack. It was main, now it's main who called function 1. And then, I'm sure you guys can guess it, if I step into the next one, function 1 just called function 2. And you'll notice that there's no data in either one of these. This data is completely empty right now. Because this function doesn't have any parameters, doesn't have any local variables, it has nothing that needs to be stored locally. Now if I do this once more, I'm now in function 3. So main called function 1, called function 2, called function 3. And then I can see I actually now have a local variable. It's an integer. If we looked at the stack, byte for byte, we'd actually see the spot for an integer in there. You'll notice right now it's set to 0 because this operator has not actually run on that chunk of memory yet. So the fact that it's 0 is just by coincidence. It just is whatever was in memory at that spot before. It could be any random value. You can't count on it being 0. So if I step over, run 1 line of code, my int turns into 42. 42 lives on the stack, remember? Now watch what happens if I step over again. Watch the call stack. Chink. So this is called pushing and popping in a first in, first out behavior. So you've got this call stack. When you push, you add something onto the top of it. When you pop, you take whatever's on the top of it off. So the top thing was function 3, is the last thing to get put in. It's going to be the first thing to come off. You pop it off the stack. And then I can just keep going, like shortcuts for this F6. And I'll finally get back to main, where it's the only thing on the call stack that we care about. And now, of course, if I step over, that's the end of this program. And it quits. Eventually it quits. Stop. Okay, the stack is a rough one. So, questions? Yep? To show how the stack works. That's the stack. So it's one of those two pieces. Here. See this? That chunk of memory right there? That's the call stack. This becomes very important. This may seem trivial right now, but it's very important. It's useful for actually executing a program. You'll see. We'll get to it. Yep? Oh, you mean why do I have to do function 3 first? Because C++ is really dumb. If I do this, it says, oh, I don't know what function 3 is. It says, you know, once again, it was designed to compile on a computer that could not hold the whole thing in memory at once. So it has to know ahead of time because it's just so dumb. And that is just purely a limitation on the ancientness of this language. There's no good reason for it. All right, let's move on to the heap. So the next chunk of memory that we're going to look at is called the heap. There's two within the user data. There's the stack and there's the heap. Stack goes downward, and this is going to be a little difficult to remember. You're going to forget this over and over again. The stack starts off at a big address and gets smaller. That's why, remember someone was asking me a long time ago when I had those two variables and I was putting out the address of them, and they were off by they were off by 4, but the one below it was a lower address. That's because the stack goes downward. Your variables will always be in descending order because the stack goes downward. So now we're going to look at the heap, which is conceptually completely different than the stack. The heap is not organized. It's just this big giant, I assume they call it a heap, it's just a big giant pile of memory. So there's a big heap of memory that's totally disorganized. The operating system manages it for you. You as a programmer never really touch the stuff. Except what you can do is you can say, operating system, from your big giant heap of memory that you've been hoarding, can I please have a little bit of it? And you specify exactly how much you need of it. I need 8 bytes of it. I need 1,000 bytes of it. I need a megabyte worth of just arbitrary data. You can change how much data you need. So now, let's say I'm getting user input. What I could do is put it on the heap and just keep expanding out the size of the heap as the user enters more and more stuff. That's how you do, variable size allocation there. So when you ask the operating system for a chunk of memory, it just hands you back the first byte in that chunk. It doesn't give you anything else. It doesn't tell you how big the chunk is. You can assume the chunk is at least as big as what you asked for. It could be bigger, you'll find out. But it gives you the first byte within that big chunk of memory. And then the advantage of the heap, the big selling point of it, is it can be any size. Yeah?
Is that how programs are when you want to program a program has to like a heap of memory?
No, not exactly. No, but you are touching on a question that I'm really surprised no one has asked yet. This is the bottom address of memory. This is the top address of memory. What's the flaw in that? They could touch in the middle. That's only possible if it uses more than 4 gigs of memory, though. If your program's using more than 4 gigs of memory, you've got other problems. What's the fundamental problem here? No?
It's like you can't hit stuff and more other stuff because the stack starts below it and you starts above it. What
do you guys see here? you see a whole ton of programs running. If every program assumes it has full access to all of memory and just go do its own thing, what happens when I launch more than one program? They don't. That's what's really cool about modern computers. So you guys will find this out in systems, but a program can assume that it has access to all of memory, that it owns everything in memory. And two programs can coexist at what they perceive as the exact same memory locations. And that's all handled by modern CPUs and operating systems. So when you're writing a program, it used to be you had to think about, like, I need to be careful not to go mess with anyone else's data. Your program has its own, your entire chunk of memory. If you've got 4 gigs of memory, your program thinks it has 4 gigs of memory. It thinks it can fill up all 4 gigs. I mean, of course, if it does, your computer kills it, and that's the end of your program. But you don't need to think about it when you're writing programs, which is really cool. That's pretty modern. It did not used to be that way. DOS did not have that, and that's why DOS, can only run one thing at one time. They had a whole bunch of really hacky, gross ways around it, but nowadays it's pretty cool. Okay, on to more heap stuff.
So what's the problem?
The problem is that this is all of your memory. Each program thinks that it has all of your memory. So if each program did, in fact, have all of your memory, then the first one would start up, it would put its stack here. The next one would start up, it would put its stack in the exact same spot and just overwrite everything you just did. And it would just be bad times. You would have a very short-lived computer. But there is a workaround to that problem. And you'll learn intimately, in more detail than you wanted, how it works in computer systems, if you go on to that. So you've got the heap. It's managed by the operating system, which means there must be some way to ask the operating system, may I please have a chunk of this memory that you're managing for me? And there is. In C++, there's the new keyword. And then in vanilla C, which is actually still used all the time in C++, there's malloc. So you'll actually see malloc in C++ code, even though it's really a C sort of thing. They both do fundamentally the exact same thing. They both reserve a chunk of memory in the heap. The operating system reserves it for you, so it knows not to give you the same chunk over again. And then it gives you back a pointer at the first byte. Okay. We have 4 minutes to go over this. I think that should be enough. We'll probably come back to this. So if I have int foo equals 42, actually let's call this on the stack. And then if I have an int star on the stack points to stack equals the ampersand of on the stack. What I've done is I've created 2 variables here, both on the stack, and this one just happens to point to this one. They both live on the stack. And I'm going to create a new one. Notice the new keyword there. If I print out, let's print out, paste, and then I print out this one. This one lives at address 0x7 something something something. This one lives at some comparably tiny, tiny, tiny address. It lives all the way at the bottom of memory. These things are off by, what, gigabytes? Billions of bytes separated from each other. But it's important to remember that right now, this stack frame, ignoring these arguments and stuff, how many things live on this stack frame? How many datas live on this stack frame? 3. 3 live here. This lives on the stack. This lives on the stack. This lives on the stack. This happens to have the value of this thing's address. This thing happens to have the value of wherever the operating system went and allocated us 4 bytes. It's going to hurt your brain. This is the thing that you can use to ask the operating system, please give me back a certain chunk of memory in the heap. So it's what gives you memory from the heap. Yeah?
If you had gone new to the stack, would it be...
You can't do the stack. No, totally different structure. Not possible to do. And that's the shortcoming of the stack. Yeah. What if you're asking me to type in ints? How many ints am I going to type in? How many ints are you going to make on the stack form? 5, 10, 20? How many? And that's the catch, is that you don't know. And you'll find out later there's dozens of other use cases. Strings are a great example of them. And that's why a direct char star is not so good, because it's fixed size. You can never change the size of that string. You can't add anything to it. You can't shrink it. It's fixed in size. And we're actually going to look at strings later. So have a great day, guys. See you Friday.